All right, so let me go back and read this one here. So number 15 says the three charged particles in figure 15 are located at the vertices of an isosceles triangle. All right, let me show a nice little picture. So I'm gonna draw that isosceles triangle here. That vertices of an isosceles triangle. Calculate the electric potential at a midpoint on the base, taking Q to be 7 microcoulombs. And it looks like here they have a Q, and then in the bottom corners, there's minus Q. So Q is a positive number, so the minus Q means a negative number. So we got two negatives, positive, 4 centimeters along each side of the isosceles triangle and 2 centimeters along its base. Now, let me use this as an opportunity to point out that the electric potential is a lot like the electric field in this sense. When we were trying to do the total electric field 2 chapters ago, so I guess this would be Coulomb's law, we said what you would do is you would find the electric field from a single point, and so number 1, and then you take that electric field, and then you find the electric field for number 2, and then number 3 and number 4, and you find the electric field for all the pieces and add them together. And so if there's n of them, we would take a sum from 1 to n of each of the electric fields. And of course, if it's like a continuous object, we have to kind of imagine breaking it into an infinite number of pieces. And so the sum becomes an integration. Now, this is kind of that same thinking, that to find the total potential, we would find the potential from one individual point charge and then add up from the first one to the nth one, however many they are. And again, if it's a continuous object, we would have to do an integration. We would imagine chopping it into an infinite number of little pieces. So for this problem, it's not a continuum, so we won't chop it into an infinite number of pieces. And in fact, we're asked to find the potential, where was it? Calculate the electric potential at the midway on its base. So right there in red. So there's no charge there, but there would be a potential from each of the negative charges on its left and right, and then there would also be a potential from the one right above. Now, notice that I didn't put arrowheads over the potential. I want to say that because one of the things that make potential an easier calculation than electric field is we don't have vectors. We just have numbers, scalars add together. And so if, took 3 plus 4, well, 3 plus 4 is always going to give you 7. But if they're vectors, 3 in one direction and 4 in another direction don't give you 7. It's only when 3 and 4 in the same direction you get 7. You could go 3 to the right and then 4 to the left, and that'll only give you a net of -1. So it's 3 and 4 in that case make -1. Or you could go 3 to the right and 4 straight up, and so the result of the 3 and the 4 is a diagonal, not 45 degrees, but a distance of 5. So the vector ones are harder to combine than scalar ones. So it's why I think this chapter 25, the math is easier than it was back in chapter 23. So maybe I even better cross that out because we're not doing electric field. I was just trying to maybe use some of the skill set that you've learned, or maybe even haven't learned, and this would be a chance to kind of review it, of what we did in 23 and how we are going to apply it here to 25. And so that is kind of my goal here. All right, so then what it would mean here is I'm going to have a potential from one charge, a potential from the second charge, and a potential from a third charge. And maybe I'll just number them, maybe starting down here in the lower left-hand corner. Here's number 1, and I'll just go counterclockwise. Here's number 2, and here's number 3. And so the key to this particular problem, and really any of the problems here, is to say, well, what is the equation for the potential from a single point charge? And that maybe I'll put up here was one of the derivations. It was Coulomb constant times the charge divided by the distance. Right? Notice not squared. The electric field was Coulomb constant times the charge over r squared. At least I should say that's the magnitude of the electric field. Then, of course, the problems got harder because then there would be components and we would have to do vector addition. But potential doesn't have the r squared, so, but it also, more importantly, doesn't have direction. So we don't have to worry about x components or y components. That makes no sense. It's actually connected to energy. And that was, if I can take you all the way back to Physics 121, that was the real important value of 121, is that when we did Newton's laws with forces and acceleration, we realized there was another option in terms of doing it with energy. And the energies were nice because they were a bunch of scalars we had together. And so that's what we're seeing here, the same pattern, but now we're dealing with electric fields and eventually magnetic fields. But it's the same logic that we could do forces and add them together in terms of vectors, or we can do scalars. And so we're following that exact same pattern that we did in 121. Now we're doing it again, but of course, our fields and our potentials are electrical in nature instead of gravitational in nature. All right, so I'm going to add these together. However, I'm going to pause here for a second. My voice is getting a little scratchy. I thought I had a little lodge. Let me run to the bathroom. Hang on here. All right, back here. Grab my throat lozenger here so that throat doesn't dry out too much. All right. So I hope I didn't spend too much time kind of giving you the thinking background, the outline, but now let's go ahead and actually do the calculation. So the potential from number 1 would be Coulomb's constant times its charge. And I'll just use the negative Q here for a moment. But we're told in the problem that Q is a 7 microcoulombs. And the distance away, and we're midpoint on the base, so this would be 1 centimeter. So let me go 0.01 and using meters, because Coulomb constant is in the units of meters, the base units, meters and coulombs. So I'll do that. And the reason I went accounting counterclockwise is I realized number 2 is going to come out to be the same thing. So I'll just double it. Okay. And so I have exactly the same thing from charge number 2. Again, notice these are scalars. The vectors, I would be tempted to say they're equal in magnitude, but opposite in direction, and they would cancel each other off. But that's a mistake here, because these are not vectors. They're equal in magnitude. In the story, they're not in opposite direction. There is no direction. So I'm just going to double it. So 1 and 2. 3 might be a little more work because I got Coulomb's constant, and I have a positive Q this time. And the distance away is this height. And so I guess I need to figure that out. Although you can see that if I took this little right triangle on the right-hand side of the isosceles right triangle, and this being 1, 4 is the hypotenuse. And so this distance here, if I just call it x for a moment, I know that the 1 squared plus the x squared is equal to 4 squared. So there's the hypotenuse. So this would be 16 minus a 1 is x squared, or x is the square root of 15. So square root of 15 centimeters, which I suppose I can get a number, and I will in a second. But I just need to know the distance away from the charge that's making the potential to the point I'm trying to calculate the potential. So square root of 15. And I'm going to put a 0.15 so that it's in meters, just like all my other problems with electric field and anything involving Coulomb's constant, because Coulomb's constant is in the base units of meters and coulombs, and seconds, kilograms. Okay, so that's it. Those are the 3 charges. So now I can put in my my numbers. You could even argue that a K and a Q is in each term. So I could factor out a K and a Q. So I'd be left up here with a -2 over 0.01, and then 1 over the square root of 0.15. And so now grabbing a calculator here, why don't I do this? So -2 divided by 0.01, add to that 1 over the square root of 0.15. And that would be that mess. So then times, and maybe I better write this down just in case you're not aware of Coulomb's constant, and more particularly the units. And so that's why I said it was important for me to put the units of meters down here. I'll come back to that, but that's the value of Coulomb's constant, 9 times 10 to the 9th, a Newton meter squared over Coulomb's constant, which is why then when it comes to the charge, I'm going to put it as 7 times 10 to the -6 coulombs. So they put it in microcoulombs, and micro means 10 to the -6. And so I need to put in coulombs to match that. So I need to put meters to match Coulomb's constant, and I need to put the charge in coulombs. And in fact, you can then begin to see that when you multiply the K and the Q together, one of the coulombs is going to cancel off, and one of the meters is going to cancel off. And so the units you would be left with, which is a Newton times a meter over a coulomb, a Newton times a meter would be a joule. And so this would be a joule per coulomb. And that is the unit of a volt. That is our definition of what a volt is. A volt is a measurement of potential. It is how much energy, joules, you would get for 1 coulomb of charge. So a joule per coulomb is a volt. So this comes out to be units of volts. Good. All right, so back to the number. This -197 is what I got from here. So let me multiply it. And so here's our 2 numbers, 9 times 10 to the 9th. And then the charge, which is 7 times 10 to the -6. And so this is a negative 1.24 times 10 to the 1, 2, 3, 1, 2, 3, and then 1 more. So that's 7. 10 to the -, 10 to the +7. So it's a negative 1.25 times 10 to the 7. Yes, we could write that as negative 12,500 million. 12,500,000 volts. Negative. And think I already called up the solutions. No, I didn't, but I got the page lined up. Let's see, this is chapter 25. Let me load it. And give it a second. Here we go. And number 15, negative 11. Now they got 11. I'm off a reasonable amount. That number is the same. We got two of them. Okay. What they use for the square roots of 0.15.
Was the question actually in centimeters or was it in meters?
Um,
Because I might have mislooked, but I thought it was in meters for a sec.
okay, I think I did something a little oddball here. I guess I need to come back and look at this, but I'll answer your question first. Let me come back and read the problem. I thought the problem was in centimeters. That's how I certainly read it in my head. And looking at the picture,
Oh,
yeah,
well, in centimeters, yeah.
yeah, okay. Um, 4 centimeters minus 1 centimeter is the square root. Oh, because it's squared. Okay. My bad. Let me fix that. I can't move it under a square root sign, that because it would be centimeters squared in square root. So I'd be off by a factor of a 0. So I mean, I need to try that one again here. So let me fix this. And I'll just fix it with a number. Square root of 15. Square roots of 15 would be 3.87 centimeters, which in terms of meters would be 0.0387 meters. And again, I got to move the decimal after I take the square root, not before. And that was careless on my part. So let me go 0.0387 here and then try this again. Okay, so negative 2 divided by 0.01, okay, plus 1 divided by 0.0387. So 174. And then times the K and the Q. So times 9 times 10 to the 9th. And then the Q is the 7th times 10 to the negative 6. Yeah, that's a better number here. So negative, and it looks like 1.10 if I do 3 significant figures. 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th volts. Yeah, and they write it as negative 11 million volts. Okay, so little math mistake right there. Apologies, but hopefully that gave you the idea of what to do. All right. Well, if you're good with that one. Oh, it looks like you threw another one here in the chat. 35. All right. Let's work through number
Yeah, 15
35.
was actually a lot easier than I thought it was going to be at first.
Yeah. Okay, so chapter 25, number 35. Okay, so chapter 25, number 35, and down the time here. Okay, so let me jump back over to the questions. 35 looks like what? Oh, now this one does look a little harder because, I think anything that's continuous, meaning we got to chop it into an infinite number of pieces and add that up. So we're doing calculus is probably harder ones. But hopefully you'll see the same strategy. Here it says a rod of length L lies along the x-axis with the left end at the origin. All right, so I'm going to make a little grid here. Here's the x-axis. Here's the y-axis. And they say you have a rod with the left end at the origin. Here's the rod. And I'll keep reading, but the picture labels it as a length L. Okay, I'm going to read it again. A rod of length L, oh, there it is, yeah, lies on the x-axis with its left end at the origin. It has a non-uniform charge density of lambda. All right, so charge changes according to this equation, alpha x. A little bigger here, where alpha is some positive constant. What are the units of alpha for A? And calculate the electric potential at the point capital A. And so they put capital A on the x-axis, a distance d from the origin, so kind of in the negative position. All right, well, I'll do the first one, not just because it's first, but it's also the easiest. It says, what are the units of alpha? So the equation is alpha x. And so usually when we do units, we put these little blocks around them. And so alpha is coulombs per meter. If you recall going, I guess, all the way back to chapter 23, we talked again in 24, and we'll see it here in 25. Lambda is kind of the universal symbol for how much charge per length. So charge with coulombs and length in meters. So coulombs per meter is what I expect here. And then X, of course, has units of meters. And I'm trying to figure out what this must be. And so the option must be Coulomb, so that you'd be left with Coulomb. And then downstairs must have meters squared in it, so that the meter over here would cancel with one of the two downstairs. And so there's, I guess, our answer. I guess we'd write it this way. The units for alpha would be coulombs per square meter. Almost sounds like a charge per surface area, but that's not what it is. That's just the appropriate units. Okay, so keeping that in mind, we can go ahead and do the main part of this problem, which is to calculate the electric potential. Now, let me start this problem just like, back over here. Okay, just wanted to see the zoom on my bigger screen, make sure it was working. Question, okay. All right, so let me start this off like I did the last problem and say, here's kind of the general idea of this chapter, that we can get the potential by adding up the potential from a bunch of points. And so 1 to n. And in the last problem, there was just 3 charges. There were point problems to add up. On this one, I guess I would view it this way. Here's this rod, and I'm going to chop the rod into little tiny pieces. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 little pieces, but in my mathematical mind, I'm going to do an infinite number of chops. And so they get closer and closer to points as I make an infinite number of pieces. So instead of saying I'm going to add from 1 to, say, 10, I'm going to be going from 1 to an infinite number. And what that really means then is I will be doing an integration. And what I will then be saying here is I will be getting the potential from a really, really, really small amount of charge that is the size of a point. Now, let me use this as an opportunity, like I did in the last problem, to say it's important that you know the derivation, or not how we derived it, but the result of our derivation that said this is the potential from a single point charge Q. It's Coulomb's constant times that point charge divided by the distance away. That's the potential. So if you imagine one of these little tiny pieces colored in green, chopped really, really thin, you would say that it has a charge of dq. That's what would go in that equation. So this is the part that I was kind of explaining. One of the tricks, if you will, that will make this chapter easier for you is that skill of learning to convert from a bunch of point charges, like 3 or 10 of them that you're adding together, to a continuum. And so it's this jump from algebra to calculus is where we started this in chapter 23, where we were good with Coulomb's law. And so that skill, if you learned it, or you're still struggling with it, well, this will help you. But if you learned it back in 23 and 24, then we're going to use that. And so this is what I was saying earlier to somebody in this Zoom session, that 25, I think, becomes a little bit of an easier chapter than we saw in the 23, because some of the skills that we learned carry over. And this is that one I was referring to, that this skill of saying, okay, I have a long rod and I'm going to chop it into an infinite number of pieces. And so instead of saying add from 1 to n, I'm going to add from 1 to an infinity. And so if I go to infinity, then it truly is becoming a point charge. And I might say the little charge is this dq. And so, like I said, that skill was first saw in 23. Now we're seeing it again. And of course, the other thing I said, and I'll say it again, what's nice about these is we don't have to worry about direction. And when we did this for electric field, that's kind of made it hard, that as we added up our points, we had to realize that there is a direction to the electric field. And we don't have that in this chapter. These are all scalars. So that's what makes it, I think, easier. So that same skill of going from algebra to calculus together with no direction, no vectors, makes this hopefully easier than what we saw in 23. Okay, so here's what I'm going to do. I'm going to put Coulomb's constant times a dq over an r in this integration. This is how I'm going to find that potential. Now that it's an integral, it's an infinite number of points. Now, this is a hard problem for this step right here, because what we had back here for lambda was written just as a lambda, but writing it in terms of calculus would say the charge density is just that, a little tiny charge in this little box divided by a little tiny distance of that box. And so this box has a size of dx, with the idea that dx is getting smaller and smaller, smaller and smaller. And so that's how we went from a summation to an interval. And so what I'm going to do is take advantage of that, move the dx to this side. Maybe I'll write it down here. So the amount of charge in this little box would be alpha x dx. The alpha x is the lambda. The alpha x is the charge density. Then I multiply by a small little distance of dx right here. That is how much charge is in that little piece. So I'll leave Coulomb's constant alone and r alone, but it's this little step right here, this dq, realizing it would be an alpha, an x dx, allows a change of variables from a dq, which came from this point charge, into something I can actually know the limits of. And that's what I'm going to do now, is change it to a dx. And so that step is the same crucial step that we saw when we were doing Coulomb's law, but we see it here, that we have to change a dq into a dx. And this part right here are the extra factors that change it from a dq to a dx. And you can see that in the definition of what is what a charge density is. If I can use a fancy word, these extra factors then that are needed to change a variable is called the Jacobian of transformation. If you're a math person and you like those big words. And so what other factors do you need as you change variables from a q to an x? And that's the Jacobian of transformation. But not worrying about the big name, hopefully you see why you need that. You're right, it's the charge density. That is the charge density times the length will give you the charge. So the charge density is the Jacobian. All right, so again, that's a big step. I haven't really even done the calculus, but what I have done is changed algebra into calculus and then changed variables within my calculus. And those are the two big steps that were, I think, challenging when we did chapter 23 and 24, and also here in 25. So it's that same skill set. All right. So we're finally getting very close to actually doing the calculus. And I will emphasize that actually doing the math and doing the calculus is the easiest part of this problem. Again, it's that skill set of going from algebra to calculus and then changing the variable. Now, I still have one more thing that I think need a little discussion before I actually do the calculus, and that's this distance away, this r. What is r? Well, r is the distance from the little chunk of charge that's making the potential to the point where we're trying to find that potential. And you can see that each chunk of charge I add up, and I've drawn one here that's green. Maybe I'll draw one that's over here that's purple. But I'm adding all these together, and you can begin to see that these ones over here near the right-hand side of the rod are the furthest away, and the ones over here near the left-hand side of the rod are the closest away. And so this r down here has something to do with where that is. In other words, the closest one has a distance away of d, but the furthest one has a distance away of d plus l, and all the other ones are something in between. Maybe it's best to write it this way: d plus x, where x is where you are on the x-axis. So starting at 0, the first little chunk of charge would be a distance of d, and then you would be adding up these chunks of charge until you got to the last one, which was at x equaling L. And so your distance away would be D plus L for the last one. And so that is our calculus. And now we can do the calculus if we realize, okay, we're going to start at x equaling 0 and stop when we get to L. And so that would be the limits of our integration. We're going to start here with this chunk at 0 and add up all these chunks. And so the position increases until we get to the last little chunk of charge, which would be x equaling L. Okay, so now finally we can get to our calculus, which, well, this one might not be a so easy one either. That looks like a solution by partial sums. So maybe I'll do the partial sums, or maybe I will just look it up. And actually, that's what I'm going to encourage you guys to do. So maybe I will do that. Here's what I mean by that. So as I go to solve my calculus, I guess the first thing I do is take a notice of things that are a constant and pull them out in front of the integral. So the k and the lambda are a constant. And so I got x over d plus x dx. And now I need to solve this. And I think this one's screaming at me partial sums. It doesn't look like a U sub. But let me take this as a moment for anybody who didn't catch it in the video. My answer for you is, and well, since we're online, my answer is a little different. Usually I tell the students that I expect you during a test to be able to do integrals that are either U subs or powers, but if they're like a partial sum or a trig sub, you can just look it up. And I give them a little table to look it up. I'm kind of curious then. I'm going to jump over to the solution. What number was this? 35. Yeah, see, the author doesn't even show how he solves it. So maybe I'll do both. Well, I don't want to bore you by going through a big math solution. So maybe I'm just going to look it up. And that's probably the best thing I can do. Let me grab the textbook. And instead of grabbing the online edition, I'm going to grab my hard copy here. But you guys all have the online edition or the PDF version that I sent you. But since I got the camera shining on it, I thought I would grab it and go near the end. You might remember that we've used this already a couple of times. This one in particular, in Appendix B here, we did the 1 plus x to the n, and we did the binary expansion on it. Actually, that's the approximation of it. I guess the expansion is over here. And so I know I sent this warning out on an email, and then I did a video on it and even showed it during the video where I got that. Okay. But let me turn a couple pages over in Appendix B. Actually, here's the next page over where the calculus starts. Here's a nice little table if you're taking derivatives. And again, the simple derivatives you probably know, but some of these trig ones, and particularly the inverse trig ones, you probably don't use often enough to have memorized. So that's why they're here. But let me go a couple pages more where they start doing the integrals. And so here it is, table B5. And it looks like 1, 2, 3. That one right there is really the one I want, right? It's got an X in the top. and it's got then a constant plus an x in the bottom with a constant here. And so I'll keep that one handy. I think that's the one we want. All the other ones got like square roots and exponentials. All right. So I'll come back to that one, but hopefully you can see then that if you take, let's see, what was it? This one here, got an X on the top. And if you take the A and set it equal to the D, and their B set equal to 1, you would have that. All right. So let me just write Coulomb's constant times alpha, and then I'll just go right to this solution, which is x over b minus a over b squared, natural log of a plus b x, evaluated from 0 to L. Okay, so let me take this again as that opportunity to say, during an exam, even during the homework where you have more time, don't bother to try to write this out as a partial sum. Can if you want. I'm kind of tempted to do it myself and have some fun with it, but I'd probably leave you with the wrong impression that you should do it and probably bore you. So I'll go back to questions. I'll do it in the break. But this then is how you would get your integration. That's what I'm after. So let's see. I'll put in now what the B meant. And so the B meant 1, and the A meant D. So A is the D and the B is the 1. And natural log, the A is the D and the B is a 1. All evaluated from 0 to L. Okay. So Coulomb's constant times alpha. All right, so let me put in the upper limits of L. So this would be L minus D ln of D plus L. And then minus this whole quantity. I'll put in a 0. So I put in a 0. That first term becomes a 0 minus a d ln, and put in a 0. That's just an ln of d. Maybe reminding myself of some properties of logarithms. And if I don't, maybe this would be a time to say, all right, again, here's that appendix B. Let me go back. Trig. For trig is probably some nice logarithm stuff. Pythagorean. Oh, where are logarithms? Here are logarithms. And so I guess on page, what is this? A9. The one I'm looking for is this property of logarithms. Whereas if you have log of A minus the log of B, that's the same as a single log of its quotient. So this is a property of logarithms that we use a lot. You may not have remembered. I'm going to take advantage of that and then say that this part right here, the L minus the 0, so the terms without the log is just that. And then this right here becomes a minus a d, well, maybe I'll do it in 2 steps. Minus a d ln d plus L. And then this minus and minus make a plus d ln of d. A alpha. Here's the L. Now, each of these have a d in it. So I'm going to factor out a d, or should I factor out a minus d? Maybe I'll factor out a minus d. I think that's
Could you
what you're
center the paper a little bit more?
Oh,
questions?
yeah. There we go. Sorry.
Yep.
So let's see. So focusing on the logarithms here. So if I factor out a minus d, this becomes ln d plus L. And then this becomes a minus, and I factored out the d, ln of d. And that's where I'm going to take this property of logarithms and say this would then just be a single log of a quotient. It would d plus L over d. And let me check. The author does one more step. The author says, well, you can divide this into d over d plus L over d. And d over d is 1. So they write it as 1 plus L over d. Yeah, that's how the author does it. I would be tempted to put that negative up in the power and invert this and say, d over d plus, well, but again, another nice property of logarithms. And that way I would have a plus sign here, but I don't know if it'd be better with it. I don't know what should be better, but since this matches the author's solution, I'll stop there. So, all right, there's how you got that one. Oh yeah, that was a good one. That was, yeah, that was a challenging one.
So why did b equal 1 when we first use that equation?
Oh, so I'm trying to do this integral. And when I look into the textbook, they had this. They had x over a plus bx. So for my integral to match their integral, I need to set their a to my d.
Oh, gotcha. Okay.
And there's nothing here, so their b to a 1.
Okay. Thank you.
And of course, you can see why they do that. This is more general, so they didn't want to put in the book something without a b in front, so that it could be more general. And they don't bother to put anything in front of this, like a c, because that can just be pulled out. So I guess anybody doing calculus would know that, so that's not an issue. All right. Well, and then for me, let me go on break. I think I'm going to solve that. And I'm pretty sure that This could be done. Oh no, this is gonna, yeah, this could be interesting. But that's for me a little later. All right. So I'll call that one quits and jump back and say, all right, what other one? Good. Now we got one on here already. Number 62 and then a 63. All right. So let me.
Michael, sorry, I was more
Yeah.
interested in 63 actually.
Oh, okay. Okay. All right. So chapter 25, number 63. And then I'll write that here. Time is 1:32, just so that we can label that in our videos. And some of these I know can be long, so let me put a page 1 on here and center this up and say, all right, so let's come back to the question. 63 must be down here near the bottom. Okay. So this one looks like another kind of same thinking as the one we did where it's continuous, and I better read it here, but I see this disk. All right, so a disk of radius capital R and has a non-uniform surface charge density sigma, which is C times R, where C is some constant and R is measured from the center of the disk to a point on the surface of the disk. Find by direct integration the potential at point C. Now this is very three-dimensional. I'm kind of looking around if I have anything that looks like a disk. I do have, how about this cap? There's a cap of my Advil bottle. How's that? All right. So I'm going to try to draw it like they have it in the picture, where I'm kind of looking at the disc on edge. Okay. But I'll do it with a little bit of an angle. And so you see this more elliptical, even though it's a circular disc, when looked up on edge, you see this ellipse. And of course, my cap has a thickness to it, and they put a thickness to it, but I think they're trying to say that the thickness is really, really, really tiny, and you're not thinking of it as a cylinder, you're thinking of it as a flat disc. If they wanted us to include the thickness here, they probably would have used the word cylinder. Okay, so mine, of course, has quite a bit of thickness compared to their picture. But notice then, I'll draw an ellipse with a little bit of thickness, and that's supposed to represent this disc. And then straight out from the center here, which I will label as the x-axis, there is some point P, which they say is a distance x. And of course, the disk has a radius of capital R. And so what they're saying here is to find this potential. Okay, now I'm going to start this problem with exactly the same comment I made for the other two. And that is to get the total potential. And what you're going to do is find out what is the potential from a single object. Okay. So first object, and then add the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, and however many you have. And if it is something that is continuous in nature, then there's an infinite number that you're going to add together, where the objects that you're adding together get smaller and smaller and smaller. They each contribute a potential. And so you have an infinitely small object added up an infinite amount of times in order to give you a disk. Okay. So that's that big step that if I could go back to the last problem we did, number 35, I was saying, look, this is that same skill set that, again, you either developed or you are developing, that kind of explains how to go from the algebra to the calculus. Okay, and so that's a tricky step, and it usually results in a DQ. So then you have to do a change of variable within your calculus before you finally do your calculus. And on the last problem, I kind of overly stated it too soon. I said the calculus was going to be easy, and it's actually a pretty challenging integral, but we just looked it up. So we really didn't have to do the hard calculus. And so the same thing is going to be here. I bet I'm going to get maybe some calculus that's hard, maybe not. But either way, the calculus itself is going to be an easy step because it's going to be really hard. I'm going to look it up, or it's going to be pretty easy and I'm just going to do it myself. But the big place is getting there. And so this is that big step here, changing it from point charges to a continuum. And then, of course, you got to keep in mind what are you adding up. And so here's what I'm going to do. So let me redraw this picture here. Let me draw the disk kind of face on for a moment. And so what that would mean is point P would be up here towards the camera somewhere, maybe right about here. Okay. And what I'm going to do here is realize, what is the equation for a point charge? Well, it's Coulomb's constant times the charge at that point divided by the distance from it. And if we're talking about a really, really small point object, we could call that a dq. So this would be k dq over r. So let's say this is the center of it. And again, point P in this picture would be way up here by the camera. Okay, so here's the point P, and I'm trying to find the distance it is back to, say, this little chunk of charge right there, dq. And then I'm going to add another dq. Now I see something clever here. What if I added all the dq's that made kind of a ring around it? Do you see how all these dq's in this ring would be the same distance away from this point P? So let me not think about the whole disk for a moment. Let me just think about adding all these dq's. So if I did this, if I said, let's do an integral of just these dq's here, they would all be the same distance away. And then I would just have this integral of dq, which would then be q, and maybe I'll put here ring. And so what I want you to realize here is because of the geometry here, instead of thinking of this formula as being Q for a single point, I can get away with exactly the same formula, but think of the charge on a ring. And because of that, I'm going to change my thinking from saying, let's not add up a bunch of points, but let's add up a bunch of rings. And so maybe I will add the first ring plus the second ring plus the third ring plus the fourth ring. So here's what I'm trying to say as I go to page 2, is that when I first started thinking about this, I was saying something like this, that the total potential, which would be the sum of a bunch of points, and since it'd be continuous, it would be the integral of a bunch of points, I'm gonna now say is an integral of a bunch of rings. And I have just figured out what the equation is for the potential from a ring. And to be quite honest, I bet your author wanted you to go back to the textbook. Let's see, that is actually an example he does. We'll call it chapter 25 in the textbook. Well, actually, I got the hard copy right here, but somewhere he does the potential from a ring. And so the dipole, there's a ring. So example 25.5, he does the electric potential due to a uniform charged ring. And what he gets is exactly this. And so he says for the ring, it would be Coulomb's constant times the charge on the ring divided by R. And in fact, he then uses this equation for the ring in example 6 to do a disk. And that's really what we're doing, except in example 6 in the book, the ring has a uniform charge density. This one is harder because it is a non-uniform charge density. So I guess what I'm getting at is, I think if you kind of were following what's going on in the book, you could start right here. You don't have to start with saying, all right, the potential total is a sum of a bunch of pieces. And if the pieces are part of a continuum, you could break it into an infinite number, and that changes it to an integral. Technically, that is integral of points, but a bunch of points the same distance away would then result in the same equation, so that you get the equation for the ring. So this step right here, from showing a bunch of points to a ring, is really what your author did in example 25.5. So I don't think this is required to do the problem, but since I'm trying to help all you, I thought, well, I'll just start from the fundamentals. And you can say, okay, this is how you get a ring. And then once you know a ring, you could say, what I'm going to do is then add up a bunch of rings in order to get the disk. And that's what we have here. We're going to add up a bunch of rings in order to get a disk. And you can use example 6, 25.6, as your example, because he does a disk. But what is different in the example 6 and the problem we're trying to do, number 63, is that the charge is evenly distributed on example 6, whereas we're told that the charge density of this thing, surface charge density, changes with R. So if you wanted to start this problem right here, I totally get it. That's perfectly understandable. That's, I think the intent that the author has in mind, to be quite honest. Start right here. All right, so hopefully that was either a good review for you or fill in some missing pieces that maybe you didn't get out of the reading or the lecture, because I know it's hard to pick this up the first time through. That's why when I always start the problem, I like to go back and show them where they came from, because you got to see it a lot of times before it makes sense. I've heard people say 3 times, but I'm not sure that's enough, or maybe 5 times, and then they start to make sense. Okay, so let me really pick up the problem right here. All right, so this is what I was doing for that rod. Remember what sigma equals. Sigma is how much charge per area. Okay. So if I'm talking about adding up a bunch of rings, if I'm going to use this equation, I want to know the charge on a ring. Well, to do that, I would be dividing by the area of a ring. And that means if I take sigma and multiply by the area of a ring, I would get the charge on a ring. And that would be my first step if I started the problem here, where, again, I think the author kind of intended for you to start. Okay, so here's my first step. I would take Coulomb's constant and divide it by R. And then right here for charge of the ring, I would put sigma times area of the ring. Okay. Now, you might have heard me say this phrase a few times, and that is make sure you're reading the math, not just doing the math. Because watch this. What does sigma equal? Well, the book says C over R. Well, don't we have an R downstairs? Yeah, but it's a different R. And that's, if you don't see it, is going to lead to a disaster. You'd cancel them off. They are not the same R's. Okay. Well, let's talk about the one in the sigma again. Let me read the question carefully here. It says that the equation for sigma, here it is C times R, where R is measured from the center of the disk. All right, so back to this page 1, where I was trying to show you I'm drawing a bunch of circles. This right here is the R. This is really the radius of the ring. Okay. So what's this R down here in the denominator? Well, where did it come from? Well, it came here from the potential of the ring. Ooh. Okay. What was that? Well, maybe we need to go back to the point here. But we got this back here by saying this R is the distance from the point of charge to where the potential is trying to be calculated, which in this picture if I came up towards the camera, this would be the point P. Or in this problem, if this is one of the rings of charges we're trying to add up, those charges would be along this distance here. So that's what this R is meaning. And so if the radius of the ring is the little r, then the distance from the charges on the ring to this point P would be x squared plus little r squared square rooted. That'd be the Pythagorean theorem. So this distance away really is this r down here. So I should probably, if I'm going to write this as a little r in the numerator, I should probably then write down here in the denominator x squared plus r squared for the potential away. In fact, now that I think about it, I probably should go back to see what the author did. Yeah. So in example 5, the author did not write this as an R to help avoid confusion. The author wrote it as a squared plus x squared, where the x is the same in his example as what we're doing, and the a is the radius of the ring. So in our case, it would be the lowercase r. So this would become r squared plus x squared. This was really a long way of saying, I'm going to switch this lowercase r into a square root of x squared plus r squared. And when you first look at that, you're thinking, wait, you're saying r is equal to the square root of x squared plus r squared? That doesn't even make sense. You're right, because these r's are different. And the way we had it written out here can be confusing. And that's why I want to straighten it out now. And so let's write everything in terms of the small r, where r is, as the author says, the radius of a ring. So that means the distance away from the charged ring in the point Q. To write it as little r, where little r represents this distance of the ring, I got to write it with Pythagorean's theorem. I got to write it as an x squared plus little r squared square rooted. All right, so that's a big step, and it really falls in under this definition of making sure you understand or read the math more than do the math. All right, so I put in my, well, and let me backtrack. So if you had started this problem with the example from the book, example 5, you would have started with the square root of a squared plus x squared. And then hopefully you would have also read the math and quickly changed an a into a lowercase r for our problem. And then everything would have been, oh, maybe a little easier to do. Okay, so back to this then. So here's the charge density, okay? Here's the distance away. Let's talk about this one now. What is the area of this ring? Now, maybe going back to page 1 can be helpful, and maybe kind of imagining this ring that I put here, maybe imagine cutting it right here, straightening it out. So this ring of charge now becomes a straight line. What is the area of that straight line? Well, it would be, how long is it? I'll put L. times its width, which I'll put W. So its area would be length times width. But what is its length? Well, its length would be the circumference around this circle. And remember, the little r here is the radius of this. So the length would be 2 pi little r. And then the thickness, the W, the width, width, not thickness, width, would be how thick is this ring? And you're trying to make it really, really thin, right? You're trying to take the limit as that gets smaller and smaller because we're trying to add up an infinite number of rings. And so we call that a dr. That's our calculus for saying, I'm going to make this really small and let it get smaller and smaller and smaller in the limit that it goes to 0. So this would be the area of a ring. Okay, so I'm going to put that here. So this would be 2 pi r dr. So again, if you started right here, I think the hardest part of this problem is to say, okay, I'm going to take a ring and I'm going to add up a bunch of rings. And this is my big substitution. What's the area of a ring? What's the charge density of the ring? How far is the ring away? So that's those 3 steps. Maybe I'll put them in parentheses so you can kind of see the 3 pieces that I did. But I think that's the hardest part of this problem. Because now the calculus comes in. And again, this is a hard integral to do, so I'm just going to look it up. But you can see that if I'm adding a bunch of rings, the first ring would be really small in radius of 0, and they would get bigger and bigger and bigger and bigger and bigger and bigger and bigger. And the last one would be the radius of the whole disk, which they told me at the beginning is capital R. So I will be adding from 0 to capital R. And so I guess I'll need a page 3 here. So finish this up. Oh, and maybe with some good timing too, because it'll be just a couple minutes before break time. So here's my integral, 0 to capital R. I'll put this back into the screen here a little bit. And maybe I'll pull out constants. So Coulomb's constants pulls out this C, they said, is a constant from the surface charge. I'll pull it out. There's a 2 pi. And then I'll be left with r squared, dr in the top, and then the square root of x squared plus r squared in the bottom. Oh, sorry, I already put the dr. There. And so this is where we get to the real calculus. Okay. And this doesn't really look like a U sub, but I bet it could be. Yeah. We could just put a U here. Well, but nonetheless, I'm going to look it up. So let's see what we have here. So let me just put Coulomb's constant C and 2 pi. Let me grab the hard copy. Grab the hard copy of the textbook and flip over to that table of integrals again. Okay, here we go. And I'm looking for something that has an r squared and then
Hey, Michael.
Yeah.
What page is that on? Just so that I can, I'm gonna write it down so I can check on
Yeah,
my
so-
online textbook too, just to note it.
oh,
Oh,
yeah. So it's, yeah.
A18.
So it's 18. In fact, I got the online one still up here because I was looking at the examples. Let me tell you, if you got the PDF, it's on the PDF page 1447.
Aha, yes, I see it now. I looked it up on my computer
Yeah.
here. 1447. Yep.
Now that I've done this, though, I don't see this one in here. This is a table that has quite a few common ones, but I would expect it to be right about here. Here's where they have the square root stuff. Here's the plus ones. Here's an X in the top. Well, that's with a minus. Oh, here we go. Here's an X with a square root plus or minus, but it doesn't have the X squared. So we might have to go to a better source. And my better source is in my office. A couple of handbooks for this, but I've got Google here. Let me just enter table. How about images? Oh, I got so many. Ones do I want? Integral, maybe I should narrow integral tables with where roots. Okay, I've got some good ones here. Not that one. Bummer. Not that one.
I looked something up, and it's
Yeah.
I just did an integral calculator thing.
Oh yeah.
Yeah, it's a very long answer though. It's kind of weird.
Okay.
It's pretty long.
Well,
Yeah.
it doesn't surprise me.
Would you want me to show you it?
Yeah, maybe. I'm kind of hoping I might have to. Oh. I got found. Oh, it's got a minus sign. Yeah, maybe I'll have to look at yours and it'll show me more if I look it up because it kept going. There's a plus sign. Oh, there's a plus sign, and then there. Doesn't have the square in the top. Yeah, bummer. This is probably a pretty good one here. Maybe I'm going to have to. Yeah, get help from you or do a little more looking up here. I am not seeing this one. But maybe this is a good example of why I say that these can get pretty hard in of themselves. So to save the work of the mathematics, we don't actually do the calculus. If I did this, integral of, I'll just spell it out, x squared over square root. Yeah, now I remember this one now, and I do remember working with some students the last time we were on campus in the office, and I was like, oh yeah, we got to look this up bigger, which easy to do when I know my own textbooks. I pulled out my old calculus one. All right, well, what'd you find here? Maybe I'll just look at yours.
Yeah, sure. Do you want me to share the screen?
Sure,
to
here, I'll
just
turn this
show you that?
off. Yeah.
Oh, it says you have to enable screen sharing.
Oh, yeah, that's right. Advanced sharing.
Let's see. Oh, there we go. Oh, wait, no, that's you. Cool. Okay. Yeah, so I put x squared over rad
Okay.
x squared plus a squared. And then so
Okay.
that's the answer that we get. This one apparently.
Ah, oh ho ho.
Yeah, kind of crazy. So negative a ln absolute value, all these absolute value signs.
Yeah. Probably absolute value is probably not an issue for us because I think everything we have is positive numbers. Oh, it looks like when you look at the solution, a lot of trig subs. Okay.
Yeah.
So, and scroll back up to the top here. So, in our case, we need to be a little careful. Their x would be our r because we're integrating dr.
Right. I could probably change it, change what we're integrating respect to just to make it easier on the eyes if you wanted. I just
yeah. So if you changed the your x's to r's and then change that a to an x.
A to an x.
Oh, and you have to change the dx.
Yeah, that's
with dr.
Here. So like that.
And then you might as well one more. Let's see. You got the you got the x. You got that's perfect then. Okay.
Yeah.
Oh, you know what? As long as you're there, put in the limits too.
Sure.
It'll simplify it. 0 to r, capital R.
My calculator can do some manual integration too, which is nice. But let's see here. It's kind of easier on the computer to type this in.
Yeah.
So compute by maximum definite integral. So I guess this is just the manually computed antiderivative. And then when you plug in the
No.
number,
Okay, so there it is, huh?
then we get something like that.
So you get r times the square root of that an x squared plus r squared, the minus the arc sinh r x squared over 2. Well, and then this
Arc-sinh. Wow.
the arc sinh though is also could be simplified, but
Yeah, I notice sometimes these websites give very complicated answers like that could usually sometimes be like simplified down.
yeah.
Or they'll do it like in a very computeristic way, following their algorithms that I've noticed it can be done usually in a simpler way and it'll give kind of a simpler answer. But I mean, technically it's correct. You know,
Yeah.
kind of ugly.
Yeah. I mean, I have the answer key open here too, and then if I
Oh, is
look
that
at it,
actually how they gave it too?
they have a C. Well, these
wow.
are these are constants that we didn't put in, I guess, but this should be the same, I think. Or actually, no, it kind of changes because here it's like a C2 pi ke, and here there's a C pi ke. So maybe there was a 2 on the denominator here in this answer somehow, and then that crossed out. So
Yeah, I'm looking at the answer now. Yeah. Well, I'll tell you what, since it's a little past our break time and I'm gonna get something to eat, why don't I call the math good? And I might take some time here to either look this up better or work it out and maybe put this last step into a video. Yeah, I think I will. You know,
For sure.
send that out later tonight. But the physics part of it, hopefully you got, and then this last math step is, yeah, a bit more of a challenge.
Yeah, definitely.
All right. Hey, well, that was a good one. All right. Well, take a break, and if you're got some more questions, we'll come back at 3 o'clock here.
Cool. Thank you, Michael.
All right, guys. See you soon. Bye.
See you.